So this is a talk, a paper actually, written by Craig Davidson and Peter of Vorenbeeth. The title is Why a Lunar Base is Better Than the Proposed Lunar Orbit Platform-Gateway to Advance Human Space Exploration. And Craig could not be here today because of pressing business, and he asked me to give his talk for him. So this is his material. Okay. I am in general agreement with his point of view. I'm not necessarily in agreement with every point. Here is, actually this is one representation of the Lunar Orbit Gateway. There's several out there because the design is not formalized, but it's a number of modules linked together in lunar orbit. And you'll notice it is smaller than the International Space Station. It's comparable in size to the Mir, the Russian space station of some time ago. But you should be aware that this station is in lunar orbit. It's not in low Earth orbit. And so the amount of launch capacity required to launch this is about 3 or 4 times greater than a comparable object in low Earth orbit. And in fact, the current NASA manifest for building the Lunar Orbit Gateway is 4 SLS launches, which is about 400 tons in LEO, which is the equivalent of 20 shuttle flights. Or 20 launches of Falcon 9s. It's enough for 20 major interplanetary missions, is to build this object. And this is another version of it. Okay, so now it's NASA's contention that this is a key piece of infrastructure to enable human exploration of the moon and human missions to Mars. As you may have heard last night when I debated this proposition myself, that's strictly untrue. And in fact, to require missions that go to the moon to go through the gateway, or Mars missions to go through the gateway, adds delta V, that is propulsion requirements to the mission, and substantially, about 1 kilometer a second to go to the moon is added, which is equivalent to increasing the launch mass of the lunar mission by about 30%. So this is a significant disability imposed on the lunar mission, and as well as on Mars missions. Craig, he actually wrote out a full paper of this, so if we do publish proceedings of this conference, you'll be able to read his thoughts in full. But he makes, the major point is, if you want to enable human activities on the moon or Mars, go to the moon or Mars because that's where the resources are. They're not to be found in free space. And so here is the Mars 2020 rover, which has an experiment on it in a method of dissociating CO2 into carbon monoxide and oxygen. Oxygen could be used for life support, it could be used for propellant. CO could be used for propellant, or it can be used to reduce Martian iron oxide to produce steel, which, by the way, is an experiment that at my own company, Pioneer Astronautics, we have demonstrated. So they're sending one of these to Mars. Once again, you're not going to find any carbon dioxide at the Lunar Orbit Gateway. And here's more detail. So this experiment is really going, this is going to Mars. And there are, this is one of the 3 chemical reactions that we had proposed for use in the Mars Direct mission. The Mars Direct mission, reacting hydrogen with CO2 to produce methane and water, electrolyzing the water to produce oxygen, and hydrogen gets recycled to make more methane. That produces methane and oxygen in a ratio of 1 to 2. That is, you could use additional oxygen to balance it, and this would give you the additional oxygen. So this is just a diagram of one block diagram of the same sort of thing. On the moon, the most obvious rocket fuel to make is hydrogen oxygen. We have now discovered ice on the moon in the permanently shadowed craters. There may even be substantial water content on the moon away from the permanently shadowed craters, underneath a bit of dirt, because the average temperature on the moon, if you average the day-night and you get, say, a meter down so that you actually get the average temperature, because the 2 weeks of light, 2 weeks of dark doesn't penetrate that deep, is about minus 50 C. The Earth would be minus 50 centigrade average temperature if we did not have an atmosphere, which gives us a greenhouse effect. So there could be some subsurface ice or at least permafrost elsewhere, but there certainly is ice at the lunar pole. And hydrogen oxygen can be made from that. Alternatively, you could bring methane to the moon and just use the oxygen. That would not, in that case, you're getting about 80% of your propellant from the moon instead of 100%, but you're dealing with an easier to manage propellant. Okay, and in fact, Craig has presented data here showing hints of water away from the pole. He notes in here, he quotes my paper on Moon Direct, where I specify having the base pretty much at the South Pole. He would like it to have it about 85 degrees south latitude. He thinks that is a preferable location. Okay, well, anyway, there's plenty of data now that's showing that there's ice in the craters of the lunar pole. Now, this is actually he took from my Moon Direct paper. Here's an idea that I had proposed on how one could get at that ice. See, the problem with the ice, and maybe this is, if we have kilopower reactors, you could use an alternative scheme. You could take the reactor into the crater. But if you didn't have nuclear power, if you're relying on solar energy on the moon, well, you have your base in the sunlit highlands outside of the crater, you have a microwave transmitter, and you're beaming power a few kilometers into the crater. And then you have a tent, which is transparent on one side, illuminized on the other. The microwaves reflect back from the side of the tent and down into the ground. Alternatively, the tent could be entirely transparent and you could just have a reflective dish behind it. Okay, that's another way to do this. But anyway, the general idea then is microwaves, of course, are tuned to heat water. That's why they're so attractive for cooking. And they would penetrate into the ground, cause water to vaporize out of the ground. And this is particularly attractive if the water is in the form of a permafrost, where it's mixed with dirt, and especially at the temperatures in these craters, permafrost could be extremely strong material. You don't want to be doing pickaxe work on it to break it up. But here we're just heating it with microwaves. The vapors come up, they go in there, there's a tube connecting it to a trailer tank, and then a rover tows that tank out. That you see, because you don't want to be hauling batteries into the crater to try to vaporize ice. That would be very inefficient. So this is a near-term application of power beaming. It's an extremely simple one because you do not need to reconvert the microwaves back into electricity, and the distances involved are modest. Well, here's this is data that he has assembled of the content of lunar soils at various Apollo landing sites. You know, for instance, A11 is Apollo 11, 42% silicon dioxide, 13% aluminum oxide. Iron oxide is 15%. Iron oxide is particularly significant because of all these different oxides. It's the easiest one to break down. You can, in other words, if you hit iron oxide with either carbon monoxide or hydrogen at temperatures of about 700 C, the hydrogen, for example, will react with the iron oxide to produce iron and water. So then the water you can electrolyze and get oxygen and hydrogen. You get your hydrogen back so you can use it again. And you get also iron, which is a useful material. One thing, unfortunately, that is in short supply on the moon is carbon. You'll notice it down there is 100 parts per million kind of quantities. Okay, that is a significant disability of the moon as a place for resources. It does have the hydrogen, which is something we didn't know 20 years ago, but it doesn't have the carbon. At least we haven't found it yet. And carbon, of course, is extremely important because we're made of carbon, our food is made of carbon, our clothes are made of carbon, our stuff is made of carbon. Or even if it's metal, it's typically made with carbon. But yes, there's reducible metals here. Okay, this is, people have been working on lunar ISRU since the 60s, actually, because it was early recognized in the Apollo period that you'd want to be able to make use of lunar resources. And there was a whole program called the Apollo Applications Program, which was designed to enable this stuff. And the thing that, since they certainly didn't know about lunar ice then, in fact, did not believe it was possible for there to be ice on the moon, but reducing lunar iron oxide, which of course was only suspected since we didn't even have samples in the early 60s, but they had good reason to believe it was there. They did work on that as far back as that time. Craig is a fan of a particular kind of lunar ISRU. In other words, hydrogen reduction, which is the kind that I'm familiar with. We've done that at Pioneer. At MIT, they did what they call a molten regolith electrolysis. Okay, and here, okay, with this scheme, it is possible to reduce not just the iron oxides, but the harder to reduce oxides like silicon, aluminum, magnesium. It's an electrolysis process that occurs with the regolith. It has to be in the molten state, which is to say above like 1500 kelvins, but then you can in fact electrolyze it and produce metal and oxygen. But you have to have materials that are capable of holding the molten regolith. And now here, he's advancing the hypothesis that you could actually separate. Well, no, I'll take that back. I think this is just a bar graph showing the fractions, because I don't believe you can separate them just by melting them, that the weights will cause them to separate. And I don't think he's saying that either. I think this is just a graph showing the fractions. But these fractions vary from place to place. Okay, now here he's citing my Moon Direct plan. This is a graph taken from my paper. And this is an architecture that I think is most appropriate for the moon if you want to take maximum leverage of in situ resources. In other words, the whole key to the Mars Direct architecture was how would you design a Mars mission architecture if you were basing it around the ability to make use of Martian resources, as opposed to just sort of introducing that capability in later. Okay. Now, Martian resources are easy to access, or at least the CO2 part are. You run a pump, you have it. On the moon, and that's why in Mars Direct we can start it on the very first mission. We send the return vehicle, it runs a pump, acquires CO2, and processes that into methane and oxygen. On the moon, it's a bit more complicated. We're having to process ice. So, but still, I want to introduce that capability as early as possible and make it the basis of the architecture. So the idea is as follows. Now, and in this graph, I show this using SpaceX hardware for the most part. And he makes the point that you could just as easily do this with New Glens instead of Falcon Heavies. They're of comparable capability. And for some of the subsequent stages that don't even require Falcon Heavy capability, one could even use Vulcans and Atlases if you wanted to. But I'll just talk it as it was originally written. Just keep in mind that it doesn't have to be SpaceX hardware that does this. Initially, we take a couple of Falcon Heavy launches, or New Glenn launches, if you will, and we use them to deliver habitats to the surface of the moon. These vehicles can deliver about 60 tons to low Earth orbit, and that with chemical propulsion translates to about 10 tons delivered to the surface of the moon. So we just one or two or maybe three. Phase one is just placing habitats and other useful hardware on the surface of the moon. One-way trip, take it, land it. Okay, that's the cargo lander, 10 tons to the lunar surface. Then in phase 2, we're beginning piloted operations. Okay, now the initial piloted operations will have to bring their propellant to come home. That is, they cannot count on ISRU. Unless you advance the hypothesis that using robots we can start the ISRU before the people go there. Or we could pre-deliver propellant, I suppose. But in any case, in these missions, we are flying to the moon with propellant. So there's a lightweight vehicle, which I don't have a specific design for it, but what I displayed here was the Apollo Lunar Excursion Module, because that's the general concept here. A very lightweight vehicle. The Lunar Excursion Module had a dry weight of 2 tons, because it didn't have a heat shield, didn't have anything. It was structurally built for lunar gravity. It's a very lightweight vehicle, okay, except that my lunar excursion vehicle, as I call it, uses hydrogen-oxygen propellant, because that's the kind of propellant we can make on the moon. And it has a total delta V capability of 6 kilometers a second compared to the 4, which is what the Apollo LEM could do. Now, with hydrogen-oxygen propellant, to do 6 kilometers a second is a mass ratio of 4, which means the total vehicle wet mass, if it had a dry mass of 2 tons, it would have a wet mass of 8. Okay? Which means if you have a cargo lander that can deliver 10 tons to the lunar surface, it can deliver the wet, that is the fueled lunar excursion vehicle, can be delivered from LEO to the surface of the moon on the cargo. It's being carried as cargo. So the way you do this is the cargo lander with the cargo of a wet LEV, lunar excursion vehicle, is delivered to low Earth orbit. Another Falcon 9, in this case, delivers a crew in a Dragon to low Earth orbit, because the Falcon Heavy is not intended to be man-rated. Okay. So, but the Falcon 9 is, and the Dragon is used to transfer the crew to the LEV. The Dragon then remains behind in low Earth orbit. Okay. And then they fly in the LEV to the lunar surface, to the vicinity where the HAB modules are, and they go and complete the setup of the base. And then they proceed to go to the crater and set up the operation to extract water from the crater, bring cargoes of water back to the base, start electrolyzing them. They can use for storage tanks for the propellant they make the big tanks on the cargo landers, of which there'll be plenty of at the base at this point. So they have a way to store the propellant that they make. Okay, so then they fly back. 6 kilometers a second takes you from the lunar surface to LEO. That is, not to do a direct entry to Earth atmosphere, which is what you could do if you had a capsule. You could just plow into the atmosphere, pop a chute, and be picked up by a boat. Here, this doesn't have a heat shield, so it does a propulsive capture into low Earth orbit. Then the crew can transfer from it to a Dragon, either the Dragon that lifted them in the first place several weeks ago, or the one that's lifting the next crew, okay, could take them down to the Earth. Okay. The Dragon has no business going to the moon. It is a vehicle designed to go through the Earth's atmosphere, come back through the Earth's atmosphere, take high G loads. None of that is necessary. It can go to orbit and transfer the crew. So there you go. So that's how those missions are conducted, until the point where we actually have propellant available on the moon. And whether that occurs after 1 phase 2 mission or 3 phase 2 missions, I don't know. But once that is an up and running thing and we have propellant available on the moon, then our mission mode changes. And now we get to phase 3, where you'll notice we have lunar excursion vehicles coming back from the moon, and they're not being expended. They're in Earth orbit. So the crew is lifted on a Falcon 9, not a Heavy, a 9, up in a Dragon, up to a LEV. The Falcon 9 can deliver 20 tons to orbit. That's enough to deliver both a Dragon and enough propellant. Okay, it only needs 6 tons of propellant for the LEV to travel from LEO to the lunar base and land. Okay, so then they fly to the moon in a reused LEV. They can come back in a LEV that is fueled on the moon, capture in LEO. So the recurring lunar mission does not require an SLS, let alone 2. It does not require a Falcon Heavy. It requires a 20-ton to LEO kind of vehicle, which is a Falcon 9. New Glenn is triple this capacity. Vulcan can do it. Even an Atlas could do it. An Ariane could do it. So there's multiple vehicles that could support this architecture, which makes it very robust in case there's a stand down. Now, in addition, the LEV has an additional capability. If you refuel the LEV on the moon, and you can do 6 kilometers a second, okay, 6 kilometers a second, if you're going to do a round-trip flight to somewhere else on the moon, requires 4 burns. Take off, land somewhere else, take off, land at the home base. 1.5 kilometers a second. That's just short of lunar orbital velocity. So you could, in fact, go from the base at the south pole of the moon all the way to the equator or anywhere in between, land, explore at a different place, and then fly back, okay, with such a vehicle. Or if you're just doing a one-way trip, take off and land, you can go from pole to pole. So that means if we set up a second base at the North Pole, now we've got the whole moon. And that's what we could do if we take advantage of. And then finally, the thing to note here is the return from the surface of the moon is direct to LEO. There's no lunar orbit rendezvous. There's no need for lunar orbit infrastructure of any kind. Now, the launch window back to Earth from the surface of the moon is always open. If you're on the surface of the moon, the Earth is always in the exact same place in the sky as seen from the moon. So unlike doing a lunar orbit rendezvous, where you have to time your rendezvous to phase with either something in lunar orbit or the Lunar Orbit Gateway or something, and the Lunar Orbit Gateway, by the way, is in this strange orbit that has a 1-month period, and only every 2 weeks will you have a window to catch it. This is like needing to take the bus instead of having your own car. Okay. No, it's un-American. Now, but now you can come back directly. You can come back anytime. You don't have to wait for the bus. And you don't have to worry about missing the bus. Okay? And that's tremendously advantageous. So this is just another graphic of the Moon Direct architecture. Okay, Mars Direct, this is also something he took from one of my charts, but this requires a heavy lift vehicle. If you could actually refuel the Falcon Heavy on orbit, because they're talking about developing refueling capability for the BFR, if you could refuel the Falcon Heavy on orbit, that 60 tons in low Earth orbit becomes 60 tons of trans-Mars injection, and it becomes the equivalent of a Saturn V class vehicle. On the other hand, or you could use the BFR. Musk talks about flying the BFR all the way to Mars and back. I suppose you could do that, but I wouldn't. I would just use it as a fully reusable 150-ton to LEO launcher, in which case you can do this and you're not expending the launcher. You're sending you're sending payloads in the 50-ton class one way to Mars. First, you send an Earth return vehicle to Mars. It refuels itself in the way we've discussed out of the Martian atmosphere. Once that's done, at the next launch opportunity, you send 2 more payloads to Mars. One is a HAB with the crew in it. The other is another Earth return vehicle, which is their backup, but which otherwise is intended to be used by the subsequent mission. So there you go. Both of these are extremely efficient architectures for human missions to the Moon and Mars, precisely because they take advantage of local resources. Now, Craig, however, does not believe that simply landing habitation modules on the Moon or Mars is adequate for creating bases at these locations. He thinks these are okay as temporary habitats, construction shacks, if you will, but rather the crews operating out of these should be tasked to build much more substantial structures. And he has an array of construction type vehicles that he thinks would be appropriate to build heavily shielded large habitats using regolith. And he calls this the armored HAB because they are radiation proof. So he sees delivering these sorts of habitats to the Moon and Mars as a way to, they are our temporary housing while we build our real housing. Okay, these are signs you can put up all over the base to tell people where they can get medicine or knives or forks or coffee or whatever. Okay, and so he has a concept for building some very substantial bases on the Moon and Mars using local materials, and that's the other thing, is you can continue to expand the base once you have the equipment. You know, give a man a house, you give him a house. Give a man a set of construction equipment, and he's got a city. A lot of this construction could also take advantage of 3D printing techniques. Well, there's just a lot in here about how he would be able to manufacture all sorts of useful things. You would think on the Moon you could get by with 3 legs to the chair, but there you go. So summary, the LOP-G, very poetic name, Orion SLS represent, well, he has pricing information, and he thinks the Lunar Orbit Gateway program would cost $5 billion a year. That's not well documented, but I do think it's plausible. If you consider the SLS program by itself, it costs $3 billion a year. Or 2.5. The Moon Direct, Mars Direct offer economical plans using existing launch vehicles and ISRU. The Armor Hab, that's his much more substantial habitat that can be built, would establish highly self-reliant, shielded lunar and Mars bases. The Moon Direct, Mars Direct, Armor Hab can be completed within 10 years within the existing budget. And I actually agree, the budget is adequate. It just needs to be spent intelligently. Thank you. So I have a couple of minutes for questions. Sir.
How much ice is available?
Well, that's a little uncertain because what we really need to do is do a ground-penetrating radar mission to the Moon. And in fact, my company, in teaming with about 4 others, has proposed a ground-penetrating radar mission to the Moon using 6U CubeSats. It's called the RISE mission, Radar Ice Satellite Explorer. We'll see if it gets selected. But whether it's our mission or another mission, I think that it would be a very useful thing to do. Because otherwise you only see the surface. And that's one reason why you might have heard the talk last night, and a guy was talking about water on the Moon, and he said, we only know about, 15 centimeters of water on Mars from the neutron spectrometer. Well, but that's as deep as the neutron spectrometer could possibly sense. It doesn't tell you what's deeper than that. Okay. Clementine had a very crude radar, but once again, it was a very high-frequency radar, 2.5 gigahertz, as I recall, very high frequency. It can't penetrate very deep. We're proposing to send VHF radar, like 2-meter radar to the Moon, which I think would be very useful because the very low-frequency radar can sound very deep, but it has very low resolution because the wavelengths are 10 meters, 20 meters, 50 meters. Talk about sending radar, UHF, 1-meter radio, VHF, 2-meter radio, can penetrate pretty deep, 10 or 20 wavelengths, and have resolutions on the order of a meter. And I think that would be useful. Yeah.
So, it's occurred to me, how do you land a bigger, one advantage of going to the lunar orbit is that it's easier to land a small vehicle on the Moon, right? How do you land your big?
Well, here's the thing. If you want to have a moon base, you need to be able to land big things on the Moon. Now, big is a relative term. I think we can build a moon base with 10-ton objects and build a modular moon base that way. I think that's adequate. And 10 tons is enough to deliver a medium-sized habitation module or carry a wet lunar excursion vehicle to the surface. And then once the base is up and running, we can still deliver more habitation modules and stuff one way if we like, but just in terms of rotating crews, we fly them back and forth in a LEV, which only requires a medium lift vehicle to fuel and send.
So you just fire your rocket, you just slow down and land?
Yeah, just like we did in Apollo. Yeah, they didn't use airbags. They didn't know about airbags. No one in the 60s had ever heard of airbags. They used rockets. Yeah.
So back on the ice at the moon. So has anybody gone back and looked at the seismometer measurements? Because that was one of the controversies of the Apollo era, was that the seismometers indicated that the moon was either made of ice or hollow. And of course, the scientists were like, can't be any ice on the moon. So then the conspiracy theorists decided that, well, it must be hollow then. And it went downhill from there.
I don't know the answer to that question. At this point, the data of the ice on the moon there's some radar data from Clementine, there's neutron spectrometer data from one of the late 90s missions, there's L-Cross, which crashed into the pole and sent up a plume that had water vapor in it, and then there's a paper that just came out last week, which was suggestive of once again, the form of measurement used could only go down a centimeter or so, but it was 30% water by weight material. Anyway, I have to close now because they've brought in the hook.